Okay, so we're going to go ahead and begin Unit 9, Forces and Motion. So we're going to talk about forces and how they act with the different objects, and talking about motion and frames of reference and things like that. So let's go ahead and begin Notes 1. I'm going to go ahead and hide here and we can begin. So to begin, let's first discuss motion. So what is motion? Well, motion is when an object changes its position with respect to a frame of reference. So that's the part I really want to emphasize here, with respect to a frame of reference. So what I mean by that is that we can only perceive motion if things are moving past us or a specific point. So for instance, let's take the example that we have here in this picture. We have a hot air balloon and a mountain in the background. Let's say the hot air balloon started here at this flag. Well, it moved east and then it went up. Okay, so to the reference point, let's say your friend was in this hot air balloon and you watched them get in the hot air balloon, and the hot air balloon went east and up, kind of like in the triangle shape, going all the way up like this. And you were standing right here watching them the whole time, and you can see just how fast they were moving. All right, so that's how we can measure motion of the hot air balloon. Now, if you're taking a frame of reference of your friend and you're standing right there, you're in different spots. But let's say you decided to climb into the hot air balloon with your friend, and you are now trying to measure the motion of your friend through that frame of reference. Well, since they're still in the hot air balloon right next to you, they're technically not moving. So they're moving right next to you the whole time. So basically, the frame of reference is really important. It's usually a stationary object which motion is compared to. So another example that I can give you is like, let's say you were driving down the road and you're on the highway. So you're driving on the highway, and then there's a car next to you that is driving the exact same speed. You might have done this like with a road trip, or like try to follow along someone if you're carpooling or caravanning with multiple cars. You might have had two cars side by side where you try to have a conversation with another car, or try to take a look at a different car. If the both cars are traveling at, let's say, like 65 miles per hour, to you it looks as if the car is not moving. But to the road, it looks like the car is moving very quickly. It's moving at 65 miles per hour. So the frame of reference actually determines how fast things are moving. So it really depends on the frame of reference. What is your reference point? That's the key words here. What's your reference point that you're referring to? We're going to watch a little clip here, a little video to show you just another example of frame of reference with some actual motion. So in this video, I'm going to show you a really quick demonstration of how we can see two examples of a frame of reference. So the object that we want to focus on here is there's going to be a ball that's being thrown up and down. And depending on the frame of reference, it takes two different paths. So let's take a look at that video.
A guy riding a skateboard tosses a ball up in the air. From the perspective or frame of reference of a stationary bystander, the ball appears to follow a parabolic curve. However, from the perspective or frame of reference of the guy moving on the skateboard, the ball appears to move straight up and down. In other words, two observers moving with respect to one another will usually disagree on the description of the motion of an object. To put it one more way, all motion is relative to the observer's viewpoint, or what we call the observer's frame of reference.
All right, so that's a very important point that we want to discuss here. When we're talking about motion, the frame of reference is the most important thing that we're kind of focusing on. Are we a bystander that's watching the skateboarder, or are we the skateboarder themselves when it comes to the motion of this ball? So it's really important to discuss a frame of reference. I have a really interesting video that I want to show you in respect to how fast we are moving through space, through outer space. Because not only is our planet moving, our planet is spinning, it's also revolving around the sun. So it's rotating on its axis, which takes about 24 hours, but it's also revolving around the sun, which takes 1 year, which is 365 days. And the solar system itself is also moving. and the solar system is moving in our galaxy, and our galaxy is also moving at the same time. So I'm going to show you this video about how we're actually moving really, really far, even though we're standing still. So let's go ahead and watch that video.
How fast are you moving right now? You might be thinking, I'm not moving, I'm sitting here watching this video. And that's true if you're measuring your speed relative to, say, the chair you're sitting in. But what about relative to the rest of the universe? Speed can only be measured relatively. When we say a car is driving at 20 miles per hour, it's really only traveling at 20 miles per hour relative to an unmoving reference point on the Earth's surface. We don't take into account the fact that the ground is moving too, but of course, it is. As we know, it takes the Earth about 24 hours to complete a rotation. The circumference of the Earth is about 25,000 miles, so if you live at the equator, you're spinning at over 1,000 miles per hour. And we're just getting started. We also know that it takes the Earth roughly 365 days to orbit the Sun. The total trip is almost 600 million miles, which means the Earth is circling at over 66,000 miles per hour. And the Sun is also moving towards other stars in the galaxy and bringing us along at about 43,000 miles per hour. At the same time, it's moving upwards relative to the Milky Way plane at over 15,000 miles per hour. In addition to all that, the Sun orbits the center of the Milky Way once every 225 million years, moving at 483,000 miles per hour to make the trip. All things considered, we're moving at about 540,000 miles per hour as a solar system. And on top of all of that, the Milky Way is shooting through the universe. If we measure the galaxy's speed relative to cosmic background radiation from the Big Bang, we find it's traveling at an incredible 1.3 million miles an hour. So you're moving on Earth, the Earth is moving around the Sun is moving around the galaxy, and the entire galaxy is moving around the universe at a combined speed of over 1.9 million miles an hour, or 530 miles every second. That means that in the time you've been watching this video, you've traveled over 60,000 miles through space.
All right, hopefully that video didn't confuse you too much. For the sake of this unit, though, we're going to mostly focus on our frame of reference being the still Earth, or if it's going to be something more specific, like if we're in a car or something like that. So we'll keep it simple in terms of our frame of reference. But for motion, there are two terms that I'd like to discuss and kind of clarify what they are. One is distance and one is displacement. So when I clarify that, I want to say that the actual path that the object takes can determine the distance it travels. All right, but the shortest distance in a line from start to finish is called the displacement, and we abbreviate it with the letter S. Okay, so I want to clarify just really quick. Distance is like the total path that you could possibly take, and the displacement is going to be from here to here. So to give you an example, let's say you were standing here at this one spot and you were trying to train your dog to stay in one spot as well. So you and your dog start right here, and you tell your dog to stay. And then you walk around the yard like this, and the dog is just watching you. Dog is still over here watching you, being obedient and staying. And you're walking around, and then you stop right here, and then you say, all right, come here, boy. And then the dog runs in a straight line. The dog is obviously not going to follow the same path you took. The dog is going to take the shortest path possible from where you started to where you finished. And that would be the displacement, the shortest path possible. Whereas the distance is going to be the total path that you took. So I have another example here that I want to show you to clarify between distance and displacement. I found this website that allows you to pinpoint any two locations. You can actually add more than two locations. And then it'll find the distance between those two locations. So I've selected Minneapolis and Las Vegas, and I wanted to calculate how much is the displacement between there. So meaning the shortest distance in a straight line. I know this looks curved on the screen, but that's because the Earth is not flat, and this is a flat representation, this map. So if this was an actual globe, it would be a straight line. So between Minneapolis and Las Vegas, this program is telling me it's about 1,300 miles, 1,300. It's exactly 1,296 between the 2 points that I selected. But let's say it's 1,300 miles. Obviously, we can't drive that. We'd be driving through a whole bunch of fields and maybe some forests through the Rocky Mountains here in Colorado and Utah. So obviously we need to stick to the roads and the highways. So if I wanted to drive to Las Vegas, I would have to select multiple different routes. The shortest route here that I can find, so let's take the shortest way possible, cutting through Nebraska. Um, it tells me it's just under 1,600 miles. It's 1,586 miles. So we've added a little over 280, almost 290 miles by driving it in on the roads versus going in a straight line. But obviously this way is not possible. So this is distance and this is displacement. So that's just another clarification. So let's talk about another clarification when it comes to forces in motion, and that's something called speed versus velocity. You know what speed is? Speed is basically how fast something is moving. It's the distance divided by the time. And we've mentioned velocity before when we talked about waves and sound waves and light waves and the speed of a wave. But to clarify even more, velocity and speed. Well, speed is the distance traveled in a certain amount of time, and we can calculate speed by doing the distance divided by the time. So let's say we drove 60 miles in 2 hours. Let's say we want to calculate what that speed is there. So if we drove 60 miles in 2 hours, the speed would be 30 miles per hour. So if you did 60 divided by 2, it's 30 miles per hour. This is usually referred to as the average speed. So whenever we drive anywhere, we know that we have a lot of varying speeds, anywhere from 0 miles per hour at stoplights or when we actually get into the car, to if we get on the highway, sometimes 70, 80 miles per hour. Hopefully not any faster than that. But the average speed is going to be the total speeds added together to get the average speed. So you take the total distance that you traveled and the total time that it took you to get there, and then that's how you would find your average speed. But instantaneous speed is a speed at a particular moment in time. So don't confuse those two. Average speed is how long, what's the average speed that it took you, so distance divided by time of the total trip. But instantaneous speed is a specific speed at one given moment. An example of that would be like a car speedometer that has multiple different speeds. Obviously, at highway speeds, we're going to be driving at different speeds depending on what the speed limit is. Moving on, though, velocity is similar to speed, but it includes one specific thing, and that is the direction an object is moving. So velocity is the speed and the direction the object is moving. It is 20 meters per second to the east. So let's say I was trying to give directions to someone and they said, how do I get to your house? Well, you drive about 30 miles and then that's it. If someone said we drive 30 miles, well, then you wouldn't know which way to go. You'd have to say 30 miles east, west. So a velocity would clarify the direction. When two objects are moving together, their velocities can be added or subtracted from one another. I'm going to show you a quick demonstration about that.
The speeds of the cars shown here may be similar, but their velocities are different because they are moving in different directions. The speed and direction of an object is called its velocity. Velocity is constant only if the speed and direction of the object don't change. A passenger seated on a bus has the same velocity as the bus. If, however, the passenger gets up and walks in the same direction the bus is traveling, the resultant velocity of the passenger is the sum of the velocity of the bus and the velocity of the passenger within the bus. To find the resultant velocity for objects that are moving in opposite directions, subtract the smaller velocity from the larger velocity. The resultant velocity is in the direction of the larger velocity.
All right, I want to recap on a certain point that the video said at the very end, and that was a term that they said resultant velocity. What I mean by that is that let's say we have this scenario here. We have a plane that's traveling through the air, and the plane says it has a gauge inside that says it's traveling at 100 kilometers per hour, and it's going, let's say, south. All right, but all of a sudden there's a headwind that it faces, and the wind's velocity is going 25 kilometers north. So what you have to do in this case is you have to add up both velocities to see what the resultant velocity is. And in this case, it would be 75 kilometers per hour. This is really important to show you why the direction is important for velocity, because if they were going in the same direction, we would get a different speed. So the question that we have here, what will be the resultant velocity of the plane if the wind had the same direction as the plane? Well, if they were both going down, the new resultant velocity would be 125 kilometers per hour. So it's really important to know the directions, because you either might be adding them or you might be subtracting them. So you could do a sketch, and the sketch would show, if we were to do this exact same thing, it would have the arrow pointing in the down direction. One other example that I have for you, when we have resultant velocity, is when people run on treadmills. Right, so oftentimes in gyms you see people running on treadmills, and let's take a look at this guy. It looks like he's running really hard. And you can see that he's actually not going anywhere. So normally, if you're using a treadmill correctly, you're not going anywhere physically in the frame of reference of the gym. So let's say this person's running at 10 to 15 miles per hour. Let's pick 10 miles per hour. And he's running to the right. That means, since he's not going anywhere, his resultant velocity is 0. That means something has to be subtracting it, going 10 miles per hour to the left. And that would be the belt on the treadmill. Same thing over here. If she's running at like 10 miles per hour to the right, the belt of the treadmill has to be going 10 miles to the left. If she's running at 6 miles per hour to the right, the belt of the treadmill has to be going 6 miles per hour to the left. So if you're using a treadmill correctly, the resultant velocity is going to be 0. So when it comes through motion and tracking objects through time, we can actually use graphical methods to represent their position. So when objects are moving, their movement can be shown graphically just like this. So this is an example of a graph. For example, we could do a distance, like in the y-axis, versus a time, x-axis graphed right here. So we have this little graph here where we show the position of an object versus time in seconds. And I want to kind of predict I want you guys to predict what's happening through all these different lines here. I'll give you a hint with the first one. So the person's, let's say it's a person running on a football field that has the lines, the yards or the meters already marked out. At the 20-meter mark, they stay there at 0. So at time equals 0 at the very beginning, they stay at 20 meters for exactly 1 second. And then at 1 second, they began to move. All right, so over here, they did not move at all, this flat portion right here. I want you to predict between times 1 and time 3 what happened here. So you can pause the video if you want, but I want you to predict what happened here. All right, so maybe you predicted that the person was moving forward, and that is the correct answer, because you can see their position in meters is advancing as time is advancing. So what does that mean between 4.5 and 6 seconds? All right, if you guess that they were moving backwards, that is a correct answer. So they went from the position 60 meters down to back to 20. Then obviously they were moving backwards. And then obviously we kind of covered this already. What does this flat portion mean when their position is not moving in terms of the time? That means that they have stopped. The final question that I have for you is, what is the total displacement of this person? All right, if you guess that the total displacement is 0, that is correct. And I know that the displacement is 0 is because they started at the 20-meter mark and they finished at the 20-meter mark. Actually, one more question for you. What is the total distance that they covered? If you said it was 80 meters, that is correct, because they went from the 20-meter mark to the 60. So that's a difference of 40. And then they went from the 60 back to the 20. So that's another distance of 40. So that's 40 meters this way, 40 meters this way. And that's a total of 80 meters. So even though they traveled 80 meters, their displacement is 0. Another thing that I want to point out here is that this graph represents meters over time, or in seconds. So this is a distance over time. Well, we know a unit for something that is distance over time, and that is velocity. So this is a chart for velocity measuring distance over time. So mathematically, we can actually apply a simple idea here that the linear slope of the distance versus time graph is equal to the constant speed of the object during that time period. And that actually makes sense here. So let's take a look at time 0 to time 1. All right, the slope of this line is 0, meaning the velocity is 0. And if you recall earlier, what we were saying is that from here to here, from 0 to 1, the person that was running this path was not moving at all. Same thing from time 3 to time about 4.5, 3 to 4.5, they were completely stopped. And that's the slope. The slope is 0. So that's their velocity. How do we calculate the slope of a line though? Like how do I find out what the velocity is here? Well, you have to find out, you have to know that the slope is equal to the change in the y direction over the change in the x direction. So what do I mean by that? I mean that it's y2 minus y1 over x2 minus x1. So yes, we will be using a lot of math in here too in order to calculate the velocity. So we're going to apply some points here. And the points that we're going to point out here are going to be the beginning and the end of that line segment. So over here you can see that we have the points 1 and 20. So 1 is being the x and then 20 is being the y. So that's our first point. And the second point is 3 and 60. So over here, so point 1 and point 2. And then we also have this formula for math class. You probably have seen this before. y2 minus y1 over x2 minus x1 will give you the slope. So if we plug in y2, so let's say this is point number 2, y2 would be 60 minus y1, so this is 20, so 60 minus 20. And then x2 would be 3 minus x1, 1, so you take the x values. You have to make sure that it's very important that you keep the points 1 and 2 consistent. So make sure if you're doing 60 divided by 60 minus 20 on the top, you're not doing 1 minus 3, you're doing it 3 minus 1. So whatever y2 is, the x2 has to correspond to that. Anyways, we do the math for that, and then we get 60 minus 20, which is 40, divided by 3 minus 1, which is 2. 40 divided by 2 is 20 meters per second. So that's how we can figure out what the velocity of that person was. 20 meters per second is actually pretty fast, so this is probably not a human running or anything like that. But maybe they're in like a motorcycle or something like that. All right, so let's do a group discussion question really quick here. What is the speed of the object between 4.5 seconds and 6 seconds? So 4.5 seconds is right here, 6 seconds is right there. So we're talking about this line segment right here. And we already discussed previously that this slope is going to represent the speed, or the velocity. So we want to find that slope in order to find the answer for this. So the equation for the slope we've already discussed is the difference in y divided by the difference in x. I'm not sure if someone's mentioned this to you before, like in math class or something like this, but this symbol, this triangle, that's called delta, that represents change in. So that means change in y divided by change in x. So to simplify that, in our math classes, we learned the equation of y2 minus y1 divided by x2 minus x1. So we have our points here. Let's see if we can plot them without actually having to write them down. We have 4.5 and 60. So 4.5 represents our x and 60 represents our y. And over here we have 6 and 20. So that's the 6 is the x and 20 is the y. So we just have to plot which one's going to be y2 and y1. So it's going to be change in y divided by change in x. So we go from 20 to 60. And then if we started from this point, we have to start from this point again. So we went from from 6 to 4.5. Okay, so just to clarify, if this was point 1 and this was point 2, let's say we were taking the y2, so you go to point 2 and take the y component, so that would be 20. y1 comes from point 1, and the point 1, the y component was 60. Okay, so that's why we do 20 minus 60. And for the x's, you take the x component from here, because this was point 2 and that was 6, and minus the x component from here because this is 0.1, so that's 4.5. You do the math, and then eventually you get a slope of negative 26.7 meters per second. Now I'm going to address what this negative sign means really quick. So we have a value of 26.7 meters per second. I would ask you, like, what does that negative represent? And some people would tell me, well, that means that they're going slower than 0. Well, you can't go slower than stopped, so that doesn't really make sense. What this negative represents is that it's going backwards. It's going in the opposite direction. So it is still traveling at a speed, but it is going in a backwards direction. So what happens when we have a graph like this where the line is actually curving upwards with time, meaning that the object that is moving, it doesn't have a consistent velocity. It might be speeding up or slowing down. Well, if the distance versus time graph curves, you must find the slope of a tangent line to find the instantaneous speed. So let's say this is like someone running, starting a race, right? At the very beginning of the race, they might be running. They're probably at the starting blocks, right? So they're not running at all. They're going very slow at the beginning once they jump off the starting blocks. But as soon as they start getting momentum, they're building up speed. It could also be a car or anything that basically accelerates. So if we want to find the instantaneous speed at a given moment in time, what we have to do is draw a tangent line. So let's do a little problem here. What is the runner's speed at 2.5 seconds? At this specific point, what is the speed? So what we need to do to this is draw a tangent line according to that point right there. So if we were to draw a tangent line to that point, then we can find the slope of this line. So that slope of that line represents the speed. So what I would do is select 2 points. So we're going to select some points right there. So we have 1, 0, and then 5, 30. So we're going to do slope is equal to the difference in the y divided by the difference in the x. And again, that's just going to be this difference in the y's versus the difference over here. So we did 30 minus 0. So since we started with this one, we did 30 minus 0. For the difference in the x, we have to start with this one as well. 5 minus 1 is what you're going to have for your x values. All right, so 30 minus 0 is 30. 5 minus 1 is 4. So if you were to do that into a calculator, you get 7.5 meters per second. So at that given moment, the speed was 7.5 meters per second. But that's not always going to be the case since this curve is turning. So let's see another problem where we check the velocity at a different moment. So here's a group discussion question. The question says, what is the runner's speed at 3.5 seconds? So before we did 2.5 seconds, but now we're going to do 3.5 seconds. All right, so the first step, again, was to draw that tangent line. So make sure you're drawing that line that is tangent to that curve at that given point where we want to measure it. Now that we have a straight line, we can begin finding the slope of that line. I'm going to find 2 easy points that we could find on that line. I'm going to select right here at the origin, and that point right there is also fine. Ideally, you would like to find a point on the other side of that tangent curve, but there's not one that really is easy, so I'm just going to select that point and then this point. So the coordinates there are 1.5 and 0, and then 3.5 and 20. So then you follow along with the same thing. So slope is equal to the difference in y which over the difference in x. So y2 minus y1 over x2 minus x1. So if we start putting in the numbers, we get 20 minus 0 over 3.5 minus 1.5. 20 minus 0 is 20. 3.5 minus 1.5 is 2. So 20 divided by 2 gives us a speed of 10 meters per second. So you can see here that this answer does change in respect to the previous time, which was 2.5 seconds. That had a speed of 7.5 meters per second. And then we jumped up to 10 meters per second. Now, since this curve is still going up, that's not the fastest that this object moves. So the speed is still going up. That is called acceleration, but we'll cover that in later notes.